two graphs that look like this, right? Let's say that I define a third function h of x that's equal to like 2 times f of x minus 3 times g of x. And we say the limit as x approaches a of h of x. That's what we're interested in. Tell me, can I do the following? Can I say that? Some people are shaking their head yes, some people are shaking their head no. So this was something we didn't do a good enough, I didn't do a good enough job on making clear. The answer to this is no. Now, usually we can do this. Why can't I do it in this case? Because I'm putting it into a discontinuity, right? You can't apply those limit laws through discontinuities like that. Now, if you have a continuous function, no problem. Go crazy with these limit laws. When we have a graph like this, you have to be real careful that you're not running into a discontinuity. So that we can't do. How would I do this instead? You have to look at the right-hand limit and the left-hand limit separately, right? So that now, since it's a one-sided limit, that always exists. Now I can push things through. So now I can do that. Oops. What is this one going to be? The limit as x approaches a from the left of f of x. Just one, right? And then what's this one? The limit at x approaches a from the left of g of x. Oh, I guess I need to put a coordinate on there. That's just 1 also, right? That's -1. If I do this piece, what's that going to be? Limit as x approaches a from the right of f of x. That's -1. How about for g of x? That's +1. So what should we say here? About the limit as x approaches a of h of x does not exist. Is everybody feeling okay about what to do with that? So again, the limit law application was a place where lots of us made this mistake, and I saw it multiple places when dealing with like functions that are graphs or doing the limit law into a discontinuity. Got to be real careful about that. Now, when things are equations, where it's much easier to, to assume continuity, like most of the time we've done this, no problem. But you got to be real careful if you're going into a discontinuity like that. Okay. Then I had this. I don't know, half dozen of us tried to use this property. Is that true? It's only true if one of or both of A and B are 0. Okay. If you're ever in doubt and you're like, ooh, is that right or not? Try just putting a number in, right? If A is 1 and B is 1, the left-hand side should be the square root of 2, but the right-hand side would be regular 2. Are those equal? No, sir, can't do that. Okay? So I caught a bunch of people doing that. Again, that happens. It's been a while. Want to make sure that we're getting up to speed. The other piece that I saw people do is like something like this. Saw this happen a couple of times. Again, never can do this. Again, if you wanted to try to check, let's just put some numbers in. Right? Different numbers can't be equal. So again, if you do some simplification, you're like, can I do that? Maybe I can do that. That looks like something I can do. Plug some numbers into what you started with and what you think it equals, and check, right? It just takes a second, and that'll guarantee for you, like if they come out to be the same, well, if they come out to be the same, it doesn't guarantee it, but it's probably good. If it doesn't work out, like almost every time it wouldn't, if it was wrong, you're in for some trouble. Like you can't do that. Numbers to stay away of when plugging in to check something like that. You know, if you're multiplying 0 and 1, like if there's multiplication involved, don't use 0, don't use 1, because they don't really, like 0 wipes away a lot of ills with multiplication, and 1 doesn't really do much for multiplication. Or if you're adding and subtracting, stay away from 0. Again, 0 doesn't do anything when you're adding. But for the most part, if you attempt to do something like this and just plug in like 2 and 3 or 1 and 2, or you're gonna get like, ooh, that didn't work out at all. Does that feel okay? By next class, I should have your tests finished and graded and ready to get back to you guys. Okay. So again, I started seeing some of these things enough times to where I wanted to address a little bit of this. We'll go through when we get the test ready to pass back in detail about like what I was looking for and like what an excellent answer would look like. But that's for later. Today, we're going to pick up in section 2.8. So we have one more day of the derivative being a hassle before we start making it way easier, and then a few days of making it way easier till it becomes a hassle again. But still better than what it was. So last time we met, we defined that we can take a derivative at a point. The derivative at the point x equals a we defined as f prime of a equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Remember that prime symbol just means the derivative, right? That's the derivative of f, or you could read it f prime. Now, if we just, instead of fixing a to a specific, or instead of fixing x to a specific a value, if we allow instead of fixing x to a specific a value, if we allow x to vary, to just be a variable, we can do the same thing, But now rather than f prime of a being a specific number, it being finite, specific, it can just be a new function, f prime of x. Okay? So there's two different ways we'll talk about doing a derivative. We'll talk about doing the derivative of a function at a point. That's the f prime of a, where a is a specific value. So the result of that is a number. And then we'll talk about the derivative of x in general. That's f prime of x. The result of that is a function. Is everybody cool with the difference? Now, the mechanics are going to feel the same, but the result, one is a number, the other is a function. Okay? F prime of a is a number. F prime of x is a function. Cool? So far, so good? Do the equations look identical except for we've replaced a with x? Yeah. So it's confusing in that regard, but all right. Let's say that we have this function f of x that's drawn, and we want to sketch the graph for the derivative of f. So the way that we want to do this is we want to start first by looking for the places on f where we have a horizontal tangent. How many places on f do you see that have a horizontal tangent? 3. Should see like one right here, and like one right there. What is the slope of a horizontal line? 0. So I'm going to plot my derivative. I know it has x-intercepts at those same 3 x values. Is everybody cool? Okay. Now what I'm going to do is I'm going to look at the slope of a tangent line for this section. What is the slope? Well, what will the sign of the slope for any tangent line from that section be? Negative, because it's trending down, right? As it gets closer and closer to that horizontal tangent, what is the slope getting closer and closer to? 0. So I'm going to have something like this coming into that x-intercept, right? Is everybody okay with that idea? Okay. How about the slope on this section? What sign will that be? Positive. Where's the slope at its highest? Probably in the middle of that section, right? If you were to estimate that slope, what does it look like? Looks like 1 to me too, right? You guys buy that? That middle section just looks like a 45-degree diagonal line. So I'll plot here 1, 1, and I know it's got to go like that. I'm going to try to make it not pointy though. That should be a smooth curve. So far, so good? No big deal so far, right? Okay. This next section is negative. Where's the steepest part at? Looks like the middle of that. You guys agree? What's the slope there at the middle look like it's about? I'd say a little less than -1, maybe -1.5 or -2. Looks a little steeper than that other section though, doesn't it? Just a little, but whatever. So I'll maybe make a point down here. It's a little less than -1. And then do like one of those. And then if I look at this section, it is positive, and it's getting positive for ever. So like that is probably a decent approximation of what that derivative's graph will look like. Notice there are only like 3 places where I definitively plotted a point for sure. Those were the x-intercepts, where I had horizontal tangent lines. Everywhere else was just kind of like an eyeballing, right? Everybody's okay? If I asked you to do a similar task on a quiz or a test, the only parts I'm looking at are the x-intercepts in the right place, and is the rest of it above or below the x-axis appropriately. Okay? So like how high those humps went, not too interested in that. Now, if you did something bonkers and went like, did like one of those, like I probably would mark you down there, because like clearly the slope isn't like 15 at that spot. But like if you're in the neighborhood, you're fine. You know what I mean? As long as you don't do something like absurd. All right. So the next example says, if f of x equals x cubed minus x, find the formula for f prime of x. So we're looking for a function. So I'll start with my derivative equation. So that's the limit as h approaches 0 of f of x plus h minus f of x all over h, right? What do I do now? Great, I plug that stuff in for f of x. Oops, that's an h. So when I plug in x plus h into f of x, I end up with x cubed plus 3x squared h plus 3, oops, I said h, I didn't write it, plus 3x h squared plus h cubed minus x minus h, and then minus x cubed minus x all over h. Questions on how I got that expression? I just FOILed out x plus h cubed and then distributed the negative through x plus h, and then I just had my minus, distributed the negative through f of x. Now, as a math teacher, I can FOIL out like a cubic in my head, not an expectation that you're doing that. If you have to FOIL that out by hand and take some steps and use some writing, that's okay. If you are able to do it in your head, feel free to do it in your head. If you remember your rows of Pascal's triangle or whatever, to do that, you're welcome to do that. If you don't remember, don't worry about it. You can just FOIL it out by hand. In general, we would not give you something beyond a cubic to FOIL out by hand. Okay? Because why? It's really time consuming. Guess what? One more section, we don't even have to worry about doing it by hand. But we got to lay the foundation first. Okay, so I've done this. What do I do next? Yeah, let's simplify. So collect some like terms. I have an x cubed and x cubed. I have a, oops. This was supposed to be a plus x, Mr. Kulik. Do you guys see why that was supposed to be a plus x? When I distribute the negative through f of x. That was would have been a big oopsie. Oop, oop. Okay, so I've combined my like terms. What else can I do? Cancel out h's. Very good. So boom, 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 boom. Now, a good question to ask here would be, Mr. Kulik, after I do that like simplifying step, am I always going to be able to cancel the h out of the bottom? You better be able to, or else you've probably made a mistake. Okay, there are some rare instances where getting that h to cancel out is actually a lot harder using the h version rather than the x approaches a version. But in general, for the stuff that you're going to be doing, if you can't cancel the h, it means you probably made a mistake somewhere, like an algebra mistake. Forgot to distribute something, you dropped a negative, you foiled something out wrong, something like that. Okay, in general, that'll always happen. What do I do now? Yeah, we plug 0 in for h. So we're left with 3x squared minus 1. That is our derivative. So this is a new idea, right? One of the few times we've encountered a situation where we have an operator that operates on a single function and outputs a function, right? Usually we plug a number into a function, get a number back. Here we're doing an operator on a function and it's returning us a function. So everybody's okay with that? Derivative being the operator there. Okay. Part B then said, illustrate by comparing the graphs of f and f prime. Okay. Well, I'm going to use this piece of graphing software here to do this rather than my calculator because it gives me a little bit better picture, certainly bigger one. So the red is my f. That's x cubed minus x. There's my derivative. Notice where I have horizontal tangents, my derivative is 0. Where I have a horizontal tangent, my derivative is 0. Where my derivative is increasing, where my function is increasing, so from like negative infinity up to here, my derivative is above the x-axis. Where my function is decreasing, my derivative is below the x-axis. And then where my function is increasing again, my derivative is increasing again, or is above the x-axis again. You guys see that? Looks right. This is a decent check. If you're not sure, graph the two and see if all the parts kind of line up like as they should. Just kind of using our eyeballs here a little bit. So far, so good? It's like, okay, Mr. Kulik, this doesn't feel dramatically different than last time. Okay, so our next one says, if f of x equals the square root of x, find the derivative and then state the domain. Okay, so the derivative, we know the equation. I'm going to skip I'm going to go straight to the plugged in version. Is everybody okay with that? Yeah, I thought we would be. Okay. Mr. Kulik, what do I do now with this thing? Yeah, use that conjugate. Very good. Excellent idea. So that's going to give me x plus h minus x over h times square root of x plus h plus square root x. Is everybody okay with how I got that numerator? If you're not, speak up and I can fill in some details, but my assumption is when I ask you that and you are silent that you're clear as to like what I did. I don't want to do every nitty-gritty step unless it's helpful, in which case I'm happy to do them, but at some point it's like, what are we going to skip showing, right? All right. What do you notice happens here? Yeah, so the x's from the numerator cancel, and then I can reduce the h out of there. So there's my simplified version. To finish my limit off, what do? 4? Yeah, okay. Just want to make sure we have two variables there. I assumed that's what you meant. What is the square root of x plus 0 plus the square root of x? What does that simplify to? 2 square root x. Great. Mr. Kulik, can I leave the square root in the denominator? Yeah, go ahead. We stopped caring about that. Basically after trigonometry. Go ahead, leave your square roots wherever you want. You go high enough into mathematics and eventually everybody's like, remember that rule where we told you like we want to write our answers this way? We're kind of getting to that point. Now, what was the domain of f? For f is including 0, right? Because I can take the square root of 0. What's the square root of 0? 0. What's the domain for f prime? Right? Can't do 0. I have only positives now instead of all the non-negatives. I just have the positives. So what's my takeaway from this? What do I notice? The domain is, it's not the same. The first one includes 0. The domain for f includes 0. The domain for f prime does not. They are different domains. Uh-oh. Is that okay? Right? Is that bad? Is that good? What does that mean? What do you guys think? Well, let's look at the graph. Maybe that'll give us a little bit of insight. So there's the graph for the square root of x, right? There's the graph for 1 over 2 square roots of x. So the very start of this function, the 0, doesn't make it in the domain for the derivative, right? When we talk about a derivative for a function, what are we really kind of talking about? Talking about slope, right? What point to the left of 0 for f of x could I use to calculate the slope? Is there another point over here to use? So it kind of doesn't have a slope there at the very first point because there's nothing to the left of it to use to make a slope with, right? As a result, that x value isn't in the derivative because I can't make a slope at 0. Because there's nothing to the left of 0 on f. Did you guys see that? What we're doing right now is we're starting to collect instances where the derivative is going to fail to exist. Right? So if you have a function that has a hard endpoint, the derivative is going to fail to exist at that hard endpoint. That's one instance where it doesn't exist. Is everybody okay with that? You can kind of see what's going on visually. Once I say it, you're like, oh, okay, yeah, sure, that makes sense why that can't work there. If derivatives are basically just slopes, there's nothing to the left of 0 on f to use to make a slope with at 0, 0. Like, okay, sure. Fine, that makes sense. Let's do this one. So I plug this in. Start with that. Is everybody okay with how I've plugged that into my formula?
Why is it not minus x plus h?
Because I distributed the negative sign through the x plus h, because the minus in front of it. Great question. You see it now? Good. All right. No, Mr. Kulak, this does not. Yes.
For minus 1 plus x over
Minus 1.
because you subtract the f from x. Negative 1 plus x.
If I wanted to put a plus sign here and distribute the negative through the numerator, I'd be free to do that. But I'm just going to leave the minus sign where it is, I think. You could do it that way, though. So Lucas is saying, could I do plus minus plus? You could absolutely do that and distribute the negative through. I wouldn't recommend it, but you're not wrong. What next? How am I going to simplify this thing? Somehow I got to cancel that h out of the denominator there at the very, very bottom. So one way you could do this is you see the two fractions in the numerator? You could make a common denominator and combine like terms and then multiply by the reciprocal to make it all into one fraction. Not wrong to do that. That's the obvious route. What I think is going to be simpler, or what I find simpler, is I would multiply the top and bottom by the least common multiple of the denominators. So I'm just going to multiply the top and bottom by 2 plus x plus h times 2 plus x. So when I distribute to the first fraction, the 2 plus x plus h cancel, right? And I'm left with 1 minus x minus h times 2 plus x. Can everybody see that? Any questions how I simplified that piece? When I distribute to the next one, I get 1 minus x, but the 2 plus x's cancel. So I have 2 plus x plus h still left. So far, so good. Notice in one shot, I got rid of all the fractions inside of fractions, right? This would be what you'd end up with if you made a common denominator, added the fractions and multiplied by the reciprocal. I basically just did it all in one shot with that technique, which is why I like that a little bit better. It's one less, it's like 2 less steps just doing that. You guys see what I did? It's okay? All right, what should I do next? Yeah, let's FOIL out the numerators, right? So let's see, what do I get? I get 2 plus x minus 2x minus x squared minus 2h minus xh. And the other one, I have 2 plus x plus h minus 2x minus x squared minus xh. Everybody okay there? Now you could distribute the negative through if you want. I'm just going to reduce, or I'm going to simplify the things, or combine the like terms without distributing. So I have like 2 minus 2 canceling out. Negative 2x minus negative 2x cancel out. I have x minus x canceling out. Negative x squared minus negative x squared cancel out. And I have negative xh minus negative xh canceling out. So all I'm left with is a minus 2h in the numerator. So far, so good. What do I do next? Reduce the h's. And my last step then would be to plug in 0 for h, which would give me negative 2 over, and I'm just going to write it as 2 plus x squared. You guys see how I got to there? Oh my goodness, guys. Great googly mooglies. Hold on a second, we made a little error. You're like, gosh darn it, Mr. Kulik, stop doing that. I missed this guy. So that should be minus 3. Sorry about that. Everybody's okay? How come nobody was yelling at me about my mistake when I missed that other H? Aaron, you saw it.
No.
It is a lot going on. Here's the good news. is we just have to get through today doing it this way. Then we're going to get the shortcuts. And you're going to be like, why didn't we start with the shortcuts? And I'm going to go, because you don't understand conceptually what's going on if you don't know what's really happening behind the shortcut. And you're like, yeah, Mr. Kulik, nice excuse. I'm just going to do the shortcut now. It's like fun. Okay. If I compare the domains for the f and f prime, what did you notice? What's the domain for f? All real numbers except for -2, right? If I look at f prime, what's the domain? All real numbers except for -2. The domain stayed the same. Okay. Second observation. The domain for my derivative can never be bigger than the domain for my function, right? If something is undefined for f, the derivative there does not exist. Hopefully that would have been obvious, but that's my takeaway from this. So if x equals a is undefined at f, the derivative there does not exist. So it'll be undefined in f prime as well. Everybody's okay? Cool. All right. Here's a fun one. So, calculus, we mentioned earlier, was the fundamental ideas were developed like in parallel, one in England, one in Germany, not to mention any place else that we might have been doing calculus. As a result, guess what? We inherit like a bunch of frickin' notations that all mean the same thing. That's what we're looking at here. So the f prime is the derivative of f. Y prime, derivative of y. Does f of x equal y? Use those interchangeably. dy dx is the differential of y over the differential of x, like the instantaneous rate of change. It's basically just the derivative again, derivative of y with respect to x. Or what we use f of x sometimes, so maybe df dx, right? F and y we get used interchangeably. Or we just put the ddx operator. That's like our derivative symbol. We put that in front, and that means take the derivative of f of x. Still means the same thing. Sometimes we use this capital D operator in front of our function. Sometimes we'll put a subscript on it in front of our function to indicate that this derivative is with respect to x, especially if that function were multivariate, if there were like x's and y's in it. The takeaway here is all of these things mean the same thing. Cross-country people, if you need to go, you can go. Just wave at me on the way out. If you have an early dismissal, just make sure you run fast today. Okay, I'm going to check your times. You too. Okay. All right. This is a definition we've been hinting at today. We're going to now write it out formally. We say a function f is differentiable at a if f prime exists. The function f is differentiable on the open interval ab if it is differentiable at every number on the interval. Notice that's an open interval, so the endpoints don't count. Everybody's okay? Differentiable just means if I take the derivative and I plug the value in, a number comes out. It's not undefined. Everybody's okay? Let's look at this function f of x. equals the absolute value of x, and decide where is that function differentiable. Okay, so let's set up our derivative formula. Mr. Kulik, how do I simplify this? Right, very good. So you remember that the absolute value of x is equal to negative x when x is less than 0, and it's just equal to x if x is greater than or equal to 0. So let's do that. So if x is less than 0, I'd say this. If x is greater than 0, I'll do this. So if I look at, distribute my negative sign through. Does everybody feel okay here? So when x is less than 0, is it differentiable? Yes. When x is equal to, or when x is greater than 0, is it differentiable? What about when x is equal to 0? No. Right? Why aren't we differentiable when x is equal to 0? Because the left-hand limit at 0 is going to -1, but the right-hand limit is going to +1. The limits disagree, so the limit doesn't exist there. And since the derivative is just a limit, the derivative fails to exist at x equals 0. Let's look at the graph of the absolute value of x and see if we notice anything going on. Oops. So if I look at this, what's the slope? Here is -1, and then it changes to +1. But at 0, the slope preceding 0 is -1. The slope following 0 is +1. That's why the derivative is failing to exist, is because the slopes don't match, right? They don't slowly change. It's just -1 until it's not -1 and changes to something else. So what do you notice about what the shape of our graph looks like at 0? What's it look like there at 0? It's like a corner, right? It's like a sharp corner. Graphically, that's what you're looking for. If you see a sharp corner, the derivative is going to fail to exist there. As opposed to something like y equals x squared, where it's a nice smooth curve That's fine, because slowly those negative slopes are getting closer and closer and closer to zero, and then they're changing, slowly getting higher and higher and higher and higher. Left-hand limit, right-hand limit both go to zero because you're slowly increasing or slowly decreasing as you're going down. But a corner, it just is until it's not. You guys see the difference? So if you see a graph with a corner, the derivative is going to fail to exist there. What other place can we, other than the absolute value, how else can we make a sneaky thing where the domain is like all real numbers, but we have places where the derivative fails to exist? What other kind of graph could I build something like that into? If Mr. Kulik is trying to trick you and build something that'll have a corner in it, and he doesn't want to just use an absolute value because he's shown you that example already, how else could I do this? With a piecewise function. Very easy to create a piecewise function whose domain is all real numbers, but at where those pieces junction together, the slopes be wildly different on the left end and the right end. Okay? So that's a critical place for Mr. Kulik to be messing with you. Okay? So keep that in mind, especially when the next test comes around. If we talk about differentiability with a piecewise function. And we'll look at some examples of that, I'm sure, in the homework here. All right. This theorem 4 is one of these that you want to have memorized. Theorem 4 just says if a function is differentiable at A, then it's continuous at A. That differentiability implies continuity. Notice that this is an if-then and not an if and only if. Does continuity guarantee differentiability? No. Our counterexample is simply the absolute value of x. Continuous at x equals 0, but not differentiable there. Everybody's okay with that? Okay. Very important that you keep that straight. It becomes really useful going forward, especially as we have a bunch of theorems that rely on continuity and differentiability, that if you have one, you automatically get the other. That's nice. All right. So, places where a derivative can fail to exist. A corner. We've talked about that already, right? A jump discontinuity, or any discontinuity, really. Because if I look at this slope and I look at that slope, those two sure are a heck of a lot different. Easy to do that with a piecewise function, right? Even if they meet, it's easy to make them so that you get like a corner out of it. The one we haven't talked about yet is if we have a vertical tangent, right? What's the slope of a vertical line? Does not exist, right? It's infinite. If we have a derivative there, the derivative has infinite slope, we'll say that derivative does not exist. Everybody's okay? What's a kind of function you've seen that has a vertical tangent in it? The canonical example is the cube root. Right? If you think about the cube root function, kind of looks like that. Has that vertical tangent at x equals 0. So that's one that you're familiar with, right? They're not easy to create without doing that. So what happens if I take f and I find its derivative and I want to take the derivative of f prime? Can I do that? Sure. That's called the second derivative. So the notation that we typically use would be like, instead of dy dx, I'd say d squared y dx squared. Or I could say f double prime. or I could say y double prime. And those are like the three most common notations. Those are the three that you'll see, are the f prime, y prime, and dy dx, and then their derivative variants. Could I do a third derivative? Or a fourth derivative? Or a fifth derivative? I could keep going, right? Okay, yep, that's right. Absolutely. Okay. So it says, if f of x equals x cubed minus x, find and interpret f double prime of x. This looks familiar, right? We did this example earlier, right? We already know this. We did that example earlier. So f double prime of x is going to just be the limit as h goes to 0 of this guy, right? If I FOIL everything out, oh no, what did I do, guys? Made a big mistake. Who sees it? Nope. Nope. Gonna leave it here for another minute before I spoil it for you guys. Nobody sees it? I didn't write the limit. You're like, oh, Mr. Kulik, that's not a big mistake. I say, au contraire, my friend. That is a big mistake. So I'll combine some like terms. All that stuff cancels out. Reduce my h's. When I plug 0 in for h, I get just 6x. So this minus 1 is that. And then this plus 1 is when I distribute the negative sign through the 3x squared minus 1. Feel okay? Yeah. Cool. So what do you notice here about the second derivative? Got a little simpler, didn't it? If your function's polynomial, that'll be the case. If it's not polynomial, maybe not. Yes, John.
So I'll say we didn't know what f prime was to begin with. Is there like a simpler way to get f double prime from just f x?
No, you can't go straight from f to f double prime without also passing through f prime. So that's a great question. Is that okay with everybody? Absolutely a good one though, right? Because these things are really recursively defined, right? I'm just going to take my previous answer and do the derivative again, take my previous answer and do the derivative. But there's not a way to go straight to the second derivative. All right. Physics. Any physics students in here? Yeah. You guys doing kinematics right now? Motion? Position, velocity, acceleration are all related in that they are derivatives of each other. Velocity is the derivative of position. Acceleration is the derivative of velocity, i.e. the second derivative of position. That's acceleration. And then, do you know what the third derivative of position is? It's named after you. This is a joke. It's jerk. Ah! Mr. Kulik, that was a good one. I know. Have I ever seen jerk used in context? Never, but that's what it's called. All right. So again, third derivatives. There's some notation. All of these things are equivalent ways of talking about the third derivative. Yuck, Mr. Kulik, why do we need so many different ways of writing the same thing? Because nobody was willing to give up their notation. And depending on the context, each of these notations is like convenient, depending on like what is you're doing. You know, if you're solving systems of differential equations or something, the dy dx is super elegant, or dealing with a related rates problem or something. Yes?
Are we going to do like given a derivative and then we're going to have to find its actual?
The original? Yes, but that's probably the end of first semester going into second semester. So we're a long ways away from that. But that is exactly the next question. Is like, okay, I do the derivative. Is there a way to recover what I started with? Natural question. The answer is yes, kind of. And we'll deal with that end of this semester, and then all through second semester is about that reversing process. All right. So if we have our f of x equals x cubed minus x, ooh, I remember that one. I remember that we already had the first derivative, and then we also found the second derivative. So if I want the third derivative, well, boy, howdy, that's a heck of a lot easier than usual. Right? Feels good. How about that fourth derivative? Can anybody do it in their head? Zero. Think about it this way. If your function is y equals 6, what does that look like? Horizontal line. What's the slope everywhere? 0! So of course the derivative of a constant has to be 0.
If you're given like the starting function, like if you go to like prime 5, you're like the just like each one after, does it like eventually get to 0?
If it's a polynomial.
Yeah.
If it's not a polynomial, not necessarily.
Why is it 0? Like, that's not exist.
Because 0 and saying 0 slope does not exist would mean infinite slope,
Oh,
right? Meaning different things, right? So 0 slope doesn't exist. It means it's just a flat line. And then, blammo, here's your assignment. So today should have been fairly okay because it was mostly just doing what we did yesterday, but we're just, or not yesterday, but last time. I'm really excited for Friday because we get to throw away the limits. We'll put them away for a while, long while, and start working on our derivative shortcuts because boy howdy, doing this difference quotient with the limit is like a ridiculous pain in the butt, especially if you have like a nasty composition of functions, like the square root of the cosine of x squared, which nuts to that. I don't want to touch that with a 3-foot pole. Not hard to take the derivative of that with your derivative rules. That's a problem you could do in a week or two. Jenny, what's up? Absolutely.